IV characteristics of the PN junction diode. I hope you can hear me. Am I audible? You may type Y in the chat box if I'm audible. Okay, fine. So this has the basic outline, PN junction diode, how the junction formation is done, and the IV characteristics of the diode. So yesterday you were expected to cover a few of the topics which were left over. So I'm covering those topics today, because that for me direct relationship and the all those explanation took a lot of time in the evening lecture. So basically, what is the conduction? Conduction is the flow of charge carriers, and because of that the power loss is there. So conduction is going to happen with the help of flow of charge carriers, and this has the power low conduction that is P is equal to I into V, that is applicable for all the devices, linear, non-linear, all the devices. So when this is combined with the conductivity equation, what we will be getting, I told you the Ohm's law says that V is equal to I into R. If I am rearranging this equation, I will be getting I by A is equal to sigma V by I, because R is what? R is 1 upon sigma, that's the resistivity, L by A, that is your R, right? So I into R is equal to V. We will be rearranging this equation and we will be getting J is equal to sigma E, that is nothing but the Ohm's law for all the things, and especially we will be using this Ohm's law for the semiconductors. J is equal to sigma E, where what is J? J is the current density, sigma is the conductivity, E is the electric field applied. What is electric field? Electric field, if you have the potential V, then dV by dx or dV by dl is the electric field applied. Fine. Okay. So what is sigma? Then this sigma comes from here. Sigma is equal to, yeah, this is written over here. Sigma is equal to NQ into mu. Sigma is the conductivity, means how the mobile charge carriers can move all together. Mobility by definition is the ability to move, that is mobility. And NQ is the total number of charge carriers. N is the density of the electrons, free electrons, which can move, and Q is the charge on each and every electron. So NQ is the total charge. So sigma is equal to NQ into mu. Mu is the mobility, how fast these total number of charges can move, that ability is sigma, right? So this is what the conductivity is. Because of this conductivity, we are having, because conductivity, what we have is J is equal to sigma E, and that can be represented in this way also. J is equal to sigma into J is equal to NQ into V bar. What is that? NQ is the total charge and V bar is the drift velocity. Drift velocity, how fast these electrons can be drift, these can move. So if V is the drift velocity for electrons, if we represent it by VE, then this is defined by VE is equal to minus mu E into E. E is the electric field, mu is the mobility. For holes, it can be defined as VH is equal to mu H into E. So by definition, this is the drift velocity. So it becomes J is equal to NQ into V. In some books, it is also represented by VD. That's the drift velocity. In some other books, it is represented by V bar. So that's the same. And for electrons and holes, generally in the semiconductors book, it's represented by nu E, nu H. That is the drift velocity. And electric field, I will be representing by E or maybe epsilon. That is the electric field we will be using. So in some books, epsilon is preferred over E. The reason and bring the electric field, that is E, English capital letter, and energy level, that is also the capital letter E. So people do not get confused by that. So some of the books are using epsilon as the electric field, while E is the energy used as the energy level. Okay, so for semiconductors, conductors, and ionic materials, what will be your conductivity for metals? Because we only have the electrons, only the electrons can move. So we have the equation sigma is equal to N E into Q E into mu E, because only electrons are existing in the metals. In the semiconductors, we have holes and electrons, both of them are there. So this becomes N Q mu N, and then this is P Q mu P, N Q mu N, and then this becomes P. P is the number of holes into Q, that is the charge. Mu P is the mobility of holes. And for ionic materials, this becomes because of electrons or holes plus because of ions. For example, some liquids are there. So what will be the conductivity? We are having the battery in which some distilled water when the sulfuric acid is there. So the ions will keep on moving towards anode and cathode. So that those are the ions, right? Like OH minus ions or H plus ions or like that. So those ions will be contributing to the ionic conductivity, right? So the complete equation for the ionic materials becomes this: sigma total is equal to sigma electronic plus sigma ionic. I hope it is clear so far. Now current in semiconductors. We are going to study semiconductors. So let us discuss the current in semiconductors. So in semiconductors, the current is found of two types. Drift is similar velocity, and that drift velocity, we told that drift velocity is V D, then Vd into NQ into Vd, the current, because so because of the drift, electrons, then NQ, then this mu B, that is the drift velocity because of holes. So the total drift velocity can be defined as this: drift velocity because of electrons and drift velocity because of holes, right? That's the drift velocity. Now you can see this is being added. This is being added because holes and electrons are moving in the opposite directions, but electrons are having, these are having negatively charged particles. So basically the current contribution is the in the same direction. That's what both of these are actually being added, means both of the currents, current due to free electrons movement and free holes movement, both of these are supporting to each other to contribute the total current in the semiconductors, and that's why we are having the added advantage of the current in the semiconductors. Another phenomena is the diffusion. What is diffusion? Let us understand. Let us have a glass of water. So you are having a glass of water. Now let's say I am going to put a drop of, some juice. So if I'm putting the drop over here, what it is going to do, it is going to go inside and it is trying to diffuse inside where the density was very less, right? So initially the glass was filled up with the water. Now I have put some few drops of milk or juice or some other thing, right? Few drops only. So what these drops are going to do, these are actually moving fast from the highest concentration to the lowest concentration. So in the glass, there was 0 concentration earlier. So these are going to move that side. So because of that, the diffusion is going to happen. These are going to diffuse, right? You can take another example. For example, you have a house, you have your room. So if you are opening the window, the fresh air will come fastly from outside environment into your through your window, right? And it will get penetrated. So that is what the diffusion is, right? So electrons will have the diffusion current that is given by Q into dn into del of n. What is the meaning of it? Q is the charge, dn is the diffusion constant for the electrons. Likewise, for holes, the diffusion current is given by minus q into dp into del of p. Del of p, it says that del is an operator. What is the meaning of del? Del is del by del x. Means with respect to the distance, how much the concentration gradient is going to happen, that is actually your del, right? So basically, how much concentration gradient is going to happen, that is going to decide how much diffusion current is seen for the electrons or for holes, right? So like you can see over here, initially the whole concentration was over here, then later on this is moving towards the concentration where the zero concentration, means the concentration gradient was seen, it is moving towards that. So in this fashion we are having the diffusion current for the semiconductors, because a junction is formed, p and n junction. So one junction is having like one part of it is finishing and the other is going to start. So of course there is a concentration gradient, right? And it is actually uh, contributing to the diffusion current. I hope you understood. If you have any query so far, you may write in the chat box. So another thing is the continuity equation. So continuity equation comes from the conservation of charge. Let's say you have a box. So whatever charge is going to enter, the same amount of charge is going to exit, right? After a particular time, because it needs some time to travel, right? So charge, incoming charge is equal to outgoing charge. That's the continuity equation. In the equation format, I have presented it in this way. I have not presented, I have taken it from book. Del P over del T, those who have investigated it, they have prepared this formula. So del P over del T with respect to time, in this time, number of holes are going inside is equal to minus P0 upon tau H. Tau H is nothing but the lifetime of holes. Tau H is the lifetime of holes. P minus P naught is the excess carrier concentration plus DH. DH is the diffusion constant into D2P over DX2, means because of the diffusion, how much del P over del T is seen, means the charge it's seen, plus minus mu H into D PE upon DX. So this is because of drift, how much charge is seen because of the drift, because of diffusion, and because of the excess charges. Okay, so what is the lifetime of the carriers? Lifetime of the carriers is this, that let's say in the one semiconductor bar, electrons and holes are there, these are moving, actually these are moving and these are striking to each other. So let's say one electron is getting vanished after the energy is lost. So that particular time is the electron lifetime. When again the energy is gained, it will again restart. And likewise, the holes will also act in the similar way. The holes will actually vanish away after some time. So that particular time is the lifetime. That is time constant is denoted by tau H and tau E. For electrons, it is tau E. For holes, it is tau H, right? And likewise, for electrons, you can see over here, this N minus N0 is the excess concentration of the charges. Excess concentration is coming because in this particular box, some electrons are coming or holes are coming. Then how much are flowing? So there will be, it was having some concentration. Let's say N0 was the total concentration in this particular box. So there will be some excess charges. So those excess charges divided by the lifetime is the contribution, like per unit time, how many charges of these are actually coming in or vanishing away, right? Plus, then because of the diffusion means the movement of diffusion and drift. These are the current formula. If you remember, for the drift current, we used to have sigma is equal to, let's talk about electrons, NQ mu n into E. Yes. So here, if you will just have a look at this, we have removed Q. The reason being the total charge. If you will multiply the whole equation with Q, left side and right side, Q will become common. That's what it is being removed from here, right? So you will be writing the equation of drift and diffusion, and then the axis charge carriers. These three are contributing to the continuity equation, and that is nothing but the conservation of charge, another form of conservation of charge for electrons and holes. That's the continuity equation. So now let's come to the main topic, PN junction diode. So before that, if you have any query, let us discuss, otherwise we'll be moving ahead. So before that, I would be revising the yesterday's concept of mass action law, N into P is equal to Ni square. What is N? If you have any query, please type in the chat box. I will take the query. In between, I will take the query. Otherwise, we will start the PN junction diode. Okay? And by the time you are just going to put the query, I am just revising the yesterday's whatever mass action law and related things we have discussed. So mass action law is N into P is equal to Ni square. What is N? N is basically the number of free charge carriers, which are electrons, right? And P is the number of free charge carriers, which are holes. Ni is the intrinsic carrier concentration at any given temperature. So this mass action law is applicable for any constant temperature. T temperature is expected to be constant because your Ni will keep on changing with respect to temperature, and also your N and P will also get changed with the temperature. Now, how these N and P are being determined? So for that, we have discussed yesterday. Let's say this is a P type of semiconductor. In P type of semiconductors, we have acceptor ions. So can you tell me what will be the acceptor ions polarity? These are positively charged particles or negatively charged ions? Yes, can you write in the chat box? Acceptor ions are positive or negative? This is having Na. This is having Nd, donor. Na, acceptor. These ions are positive or negative? Positive. Somebody is writing. Anjana is writing positive. So look at this. P stands for positive. That is for whole. Means whole particle is the positively charged particle. We are having that thing in our mind. So Na, for example, aluminium. What aluminium is going to do in the outermost cell, there are 3 electrons. So 4 silicon electrons will come together to form the bond, and one silicon atom is actually coming there, but aluminium is not having that particular electron. So what it is going to do, it is going to take this electron from the free space. Some like intrinsic charge carriers were there, right? So it is going to take that electron. So if the electron is taken on aluminium, how many proteins were there? Proteins means positively charged particles were there, 13 in the nucleus. Now this electron came from somewhere else. So how many negative charge particles are there? 14. Now tell me, what is the valency of this aluminium now? This is positive ion or negative ion? So in order to find out the ion, we will actually add the positives and negatives, and whatever is left over, that is our ion, right? So when you are going to add both of these, what you are getting? -1. Correct? So basically, aluminium is negatively charged ion. Na is negatively charged ion, and we will represent it by minus. Am I correct? Yes. Likewise, for N-type material, we will have all the things. I'm removing all these things. So aluminium, which is trivalent impurity, that is negatively charged ion, and Na, acceptor, we will represent. So all acceptor ions are negatively charged particles. Charged, not particles. We'll call that those ions, right? Because these are heavy, right? So I'm removing this now. Likewise, for P-type, we will have Nd. So Nd will be having 5 electrons. So 5 electrons, for example, phosphorus. So phosphorus is going to share the 4 electrons with all the silicon, right? It is going to share the 4 electrons with silicon. Now 1 electron is extra. That electron actually is not needed more by phosphorus now. So what is actually is going to happen with Nd ions? These Nd ions, for example, phosphorus. This is having the element in the periodic table. Its number is 15, means 15 protons are there, right? We are not talking about neutrons because those are only contributing to the weight of that particular element, right? But that is not contributing to the positive or negative charges. And the current conduction is only going to happen with the help of charges, right? So we will not consider the neutrons over here. So these were 15, but we just need 14, right? So we just need 14 electrons. Positive were 15, negatives are 14, because one of these is given away. This is the free space of the material. So that becomes the free electron, which came from the phosphorus, right? So basically, 1 electron which is taken away from phosphorus, that is going to lead you positive 1 valency. That's why all the donor ions are positively charged particles, positively charged fixed ions. We'll call these fixed ions because it is somewhat like that. In one room, you have windows, you have other fixed things you cannot move. Likewise, in a structure of the material, ions are fixed, you cannot move. When it can be moved, only when the destruction is surely possible, then only you can move, right? Otherwise, in simple category, it cannot be moved. You can move in your things you can move in your room. You can move your books, your pen, your all the light things you can move, right? Lightweight things. So lightweight things in the material are electrons and holes. You can move all these things, and these are contributing to the current. Only the destruction is going to happen, then ions are actually moving. So once the destruction is going to happen, the room is not the same room. For example, some earthquake is coming and window is actually moved from its original space. So now that room is not that the same one, right? Means we cannot reuse that thing. Likewise, the materials cannot be, this p-n junction cannot be reused if the ions started moving in some critical case, right? So for example, avalanche phenomena is one of them. We'll discuss that. Okay, so I hope you understood what is Nd and Na, why these are Na is negatively charged particle and Nd is positively charged ion, right? So now let us consider the mass section. We will consider now the equilibrium of charge. So in this, let us consider there is a semiconductor bar as shown in the diagram. It is having some P and some N doping also, means Na and Nd, both type of doping is done. Now what type of material it can be considered? So in order to consider the type of material, what we have to do, we have to take it like Na minus Nd. If it is positive, it means it is p-type. If it is negative, we will consider that this is n-type. Okay, that's the formula. Now for any semiconductor, what we have to do, we have to figure out the charge neutrality equation. So this is again coming from the conservation of charge. See, we have n is equal to approximately Nd. N is equal to approximately Nd, right? Let's say this particular semiconductor is having Nd doping much more greater than Na, right? Nd is, right now we have considered this is positively charged ion. N will be having negative. N are the electrons, right? Now, if P was in minority, so minority carriers, P is equal to Ni square upon Nd. We will consider the minority carriers in that way, that your P is equal to Ni square upon N. That is nothing but Nd. In this manner, I will consider my P, right? So P is positively charged ion. If some Na was also there, then basically the equation becomes Na is again negative, right? So N plus Na is equal to P plus Nd. This is the formula which says that positive and positive is added together and negative is added together, all the charges, and this is the equilibrium condition, charge equilibrium condition. So this is how this will be taken up. Now the next one is, I'm going to erase this all, PN junction. So in PN junction, one is P and another one is N. There are two semiconductors. These two semiconductors are brought together. This is P type, this is N type. These are brought together and then these are joined. So this becomes the PN junction. So being a first year guy or maybe BTech from any branch, you can just understand that there is one break which is having the P type, another break is having N type. We are bringing all them together and then this becomes PN junction. That is as a layman, right? But as an engineer, electronics engineer and the faculty members, you should understand that it is not done in that way. You cannot join two breaks unless until some other material is going to come in between. If some other material is going to come in between, it means it is no more that particular only P and N junction. Some third layer is also coming in between. For example, we are constructing, so two bricks can be attached with the help of some concrete, right? So the concrete is the third material, and we are not permitting any third material over here. So what we are going to do, we are utilizing whatever we have just discussed. We'll be taking one substrate which is either P type or N type. So let's take it P type. Okay, we have taken it P type. So this is completely doped with the P type. Let's say this is doped with Na is equal to 10 raised to power 15 atoms per centimeter cube. Now from another side, I will try to do N type, and this, let's say I'm going to diffuse till 10 or 18. So since, let's say I'm going to diffuse from that so that you can see it in a good way. So let's say this is the portion in which I have diffused the N type or the donor impurities. Now the donor impurities are more as compared to the acceptor impurities. If you will subtract both of these, you will find that this is nothing but 10 raised to power 18 only. Try to subtract 10 raised to power 18 minus 10 raised to power 15. What you are getting? Can you give me the answer? 10 raised to power 18 minus 10 raised to power 15. How much you are getting? Please type in the chat box. I'm waiting for your answer, please. 10 raised to power 18, which were the donor impurities, minus 10 raised to power 15, which is the acceptor impurity. What is the answer? So the answer is 10 raised to power 18 only, right? Because I can make it like 10 raised to power 18 into 1 minus 10 raised to power 15 is 10 raised to power 18 into 0.001. So this becomes actually 10 raised to power 18 only. So the impurity, if we are having a little higher than whatever P type you have, let's say even if this is 10 raised to power 16, then 0.01 you have to subtract. If this is 10 raised to power 17 P type, then you have to just subtract 1 minus 0.1. So it will become 0.9 times of 10 raised to power 18. So basically that concept is taken and this is how the PN junction is formed. Okay. So the PN junction is formed in this way. Please type Y if I am audible. Please type Y in the chat box if I am audible so that we can start. If some issue is there, we will check for the issue. In the PN junction, this is P type, this is N type. How it is prepared? The P type substrate is taken completely or N type substrate is taken completely. And other side of that is diffused by the another type. N type diffusion is done. let's say y, this p was the p was the number of p was the substrate. So n-type diffusion is taken from the other side wherever we want to make it n side, and this is how the p-n junction is formed. This is the p-n junction diode symbol. So how this symbol is coming up? So let us discuss how this symbol is what it is going to symbolize. P are the holes. Holes are positively charged particles. Holes are having positively charged particles. N for electron. Electron is negatively charged particle. So electron is negatively charged particle. So this symbol, if you just take it in this way, let me take it in this way. This is your P and this is your N. P for positive and N for negative. So this triangle of P is taken and this particular vertical standing from N is taken. This portion, only this portion. And that's how it becomes the symbol. So this P triangle shape is showing that this is to be connected to the positive terminal. And this straight line says that it has to be connected to the negative terminal for the normal operation. Okay. So this triangle shape is P side, and this standing line is N type, which is denoting to the negative of the power supply in order to make the diode on. Correct? Yes. Now let us proceed. So for P and N junction, you have P-type material, which is having these red circles are actually holes. These are holes. And these are fixed ions. So somewhere in the material structure, you will be having these Na ions, acceptor ions you have. And here likewise in the N type, you have Nd, which are positive fixed ions, and other ions, others are silicon. These which are not having any charge, those are actually silicon. And these are having some electrons running. Okay. So basically, these are the majority charge carriers. Majority charge carriers. This is P type. So we can denote it by PP. In some books, it is only denoted by P. In other books, it is denoted by PP. PP means it is majority charge carrier in the P type. While this is denoted by either only N, small n, or in some other books, it is denoted by NN. Like in Millman Halkas, it is denoted by NN. So this NN means this is majority charge carrier in N type. Okay. So minority charge carrier, how you can figure out? You know the formula for the minority charge carrier. Ni square is equal to P into N. So minority charge carrier, for example, for this, you can represent it by Np is equal to Ni square upon Pp. P is nothing but, and you can get it for this, right? Now, basically, here you have these are the fixed ions, like windows in your room, because these are the fixed ions. And these are holes. These are able to move. These are is somewhat like this, that the particles are diffused, just like a drop of milk, I should say, or juice in the water, because water is transparent, so we can visualize that. But if we are putting only, the reason being have a good content of water, so that's what we have taken the example of juice and water, because that's visible, it is having some color. How the picture formed, that's going to happen. Look at this. These are going to move this way. Why these are going to move in this way? The here holes are going to exist. This is N type. So in n type, we have minority holes, and that can be represented like this. Pn can be represented as Ni square, small ni square. That is the carrier concentration, intrinsic carrier concentration divided by Nd. So more the doping, less number of holes are there, very less number of. So intrinsic, we used to have 10 raised to power 10 order. If I am going to make it 10 raised to power 18 order doping, 10 raised to power 18 order doping, then how many holes are seen? Approximately 100 holes in this particular structure, right? So that is very low concentration as compared to this heavy concentration that can be terraced for 15, 17, 18 or somewhat like that. So this can be actually, here the number of holes are more, and here the number of holes are in inside, the number of holes are lesser. So the diffusion is going to take place from left to right side for the holes, and for electrons the diffusion is going to take place from this to this way, opposite direction of this. What it will lead? Holes are moving from their original position, which was the majority place, to the another place which was minority, and electrons are moving across the other side. What it will be doing? It will make the depletion region. How it is going to make the depletion region? Let us understand. So the depletion region means depleted from the charge carriers. It is formed in this way. Let's take this particular region which is very near to the junction. Okay, so this is one electron seen over here and another electron is seen over here. This electron and hole are crossing to each other, and then these are going to see to each other. So these are getting recombined. Once these are being recombined, it means movable particles are not existing. Electron and hole was the only particle which was contributing to the current. So I'm sorry, I don't know how, but this actually got disconnected. So let us start wherever we were left. Yeah, now it is there. So what I was discussing, the last topic, if you can just. Yeah, my screen actually, I don't know, internet connection or something else. So now that the voice is back, I'm back now. Yes. Information. This is going to from this to this hole and electron. These are coming sideways. So what it will be doing is hole and electrons will get recombined, and this is known as recombination. This is behind the fixed ions. positively charged ions and negatively charged ions. Left side, these are negatively charged ions which were accepted impurities. Right side, these are positively charged ions which are nothing but the donor impurities. So you can represent it in this way. This is the junction. These are the negative charged ions and these are the positive charged ions. What we know, if one side the negative charged ions are there, other side positive charged ions are there, we can consider that this is going to form just like a capacitor. Can I say it like that? Because both sides, the junctions are actually the conducting junctions are there. So basically this from this to this is the region which is depleted from the charge carriers. In order to see the statics inside this, the details, what you can do, you can go with the Poisson's equation. So you can just solve it and you will find that the electric field in this particular region is going to take place in this way. The electric field is going to, because this is going to take place in this way. The integration of electric field is going to give you the built-in potential. So if you will integrate it, you will find that it is going to give you this type of shape for the built-in potential. So the potential is going to start from 0 and then it is having some height. Okay, so this way you will be having your built-in potential. You can see the built-in potential is having higher towards the N side and lower towards the P side. So it means the forward bias was positive towards this side and negative towards this side. This is your P type and this is your N type. So can I say this built-in potential VBI, this is going to oppose your forward bias. You understood this? There is a built-in potential. The built-in potential comes because the left-hand side acceptor ions and right-hand side donor ions, positive. These are in the depletion region. These are only concentrated. So that particular region is not following the charge neutrality condition because P and N, both of these are getting 0 over there. So it means left side you will have the negative charge and right side you will have the positive charge. So when you will solve the Poisson equation, then the solution will come that there is some disturbance, so some electric field is existing through this region. So this will come in the triangular shape because this charge is actually going to increase. This is constant, right? So you will be getting the straight line in both of the sides. Electric field will be, this is the electric field, that is the straight line, and this is straight line of the electric field. When you are integrating the electric field, you will be getting VBI, built-in potential. So starting from 0, you are having this to some value. This particular height is actually the built-in potential. That depends on the doping concentration of P type and N type. Yesterday that was discussed, that there is some log formula, and with the help of that we can have. Okay, so that's the built-in potential. VT log NAND upon NI square. That's the built-in potential formula, right? So that built-in potential, what it does basically. So this built-in potential actually is going to oppose. You can see over here towards the N side it is positive. Towards the P side it is 0. Built-in potential is 0. Forward bias means P has to be positive and N has to be negative. It means this built-in potential is always opposing the forward bias or the normal operation of the diode. So if it is so, it means this built-in potential has to be crossed. Then only the diode will work, right? Okay. Yeah. So for this, you can understand from the energy band diagrams. So this is the N type and this is P type. What we have discussed yesterday, for N type, the EF, that's the Fermi level, that is towards the conduction band, because the probability of finding 50% electrons is more towards the conduction band. But for holes like P type, the probability of finding the electrons or holes is more towards the valence band. So you can see the EF levels are differing. If you are preparing both of these materials all together, what is going to happen is you have to adjust this Fermi level. So bringing this down will also bring down this and this. So it means this is brought down this complete structure is broken down. Kitna, how much we have to brought it down? Let's say this is delta V. So we have to brought it down delta V. So these are getting shifted with delta E. In the same proportion, the EC and EB are being shifted, right? So here you have the ample number of electrons, and here you have ample number of holes, right? And these are the ions, positive ions and negative ions. These are the ions. So this region, particular region is being depleted. So these electrons, if I want to make a movement of these electrons towards this way, it cannot be possible because this long barrier is there. Physical distance of the depletion region is big, along with the height. This is known as the barrier height. We are taking it in electron volts. Energy is in electron volts. So if you can recall the formula, energy is what? Potentially is defined as V is equal to W by Q, work done per unit charge, right? And work done is nothing but energy. So E is equal to Q into V. Q is negatively charged particle. So basically E is equal to minus Q into V. So if you are just removing this electron volt, if you are removing this electron and you are making it negative, then this becomes the potential. Simple, very simple. So basically this is the height. You just find out the difference between EC, that is going to give you the height of this barrier. Okay. So this much of barrier is seen by these electrons, and these are not able to move and cross this junction. So it means the current is not going to flow in the normal condition. So for PN junction energy band diagrams I have shown over here. This is in the normal condition. P side, it is energy level. This is P side, left side, and right side we have N. So these are having the ample number of holes. These are having ample number of electrons. But these electrons cannot move this way. There is no good movement in this way. The reason being, this is the barrier height, right? From this to this is the barrier height. And along with that, there is barrier this, right? Horizontal was the depletion, region width. So height is more, width is also more. These electrons are not having good enough energy to cross this barrier. So what is going to happen? The current is not going to flow, or very less amount of current, negligibly small amount of current is going to flow, because only few of them can have that particular energy. For example, if I'm asking you to cross the barrier of, let's say, 5 meters and let's say 10 feet. So maybe any one of you can cross that particular barrier, but not all. Or if I'm reducing that. So it means normal people cannot cross that barrier, right? So likewise, these electrons are not able to cross this barrier. That's what in equilibrium there is no current flow. Now let's make it forward bias. If we are making it forward bias, means we are applying positive voltage P side. Positive voltage P side, it means minus EV. V is the voltage, and that much of energy you are putting. It means energy bands will go downside. So these energy bands are going downside, but the N side was fixed. This was attached to 0. So this is not changing its level. So the Fermi level will get shifted according to the applied energy. Applied energy, the Fermi level is getting shifted. So now you can see the barrier is actually, the barrier height is lesser. So more electrons can move. Okay. If you are making it more, it comes in the aligned. In this situation, whenever it comes, it means these electrons can freely move and the current starts flowing and without any hindrance in the forward bias, right? If we talk about reverse bias, just take the very left side of it. Reverse bias means we are either making the P type negative or N type positive. So let's take P type negative voltage we are going to apply and keep the N side grounded. Negative means minus E into minus V. It means I am going to apply the positive energy. Positive energy means it is going upside. So you can see the Fermi level has actually risen upside according to the applied voltage. So it means we have increased the height of the built-in potential, which was already over there, which was a big barrier. We have increased that height. It means there is no possibility to cross this barrier by these electrons, and that's how the current in reverse bias is not going to flow. Okay. So this is with the charge density, how the charge density is seen and how the potential is changed. So in first one is, look at this. This is positive for p type. This is p type positive, and this is n type negative. So in the positive, we have connected the battery to the positive. This is the depletion region where only the negative ion fixed ions and positive ions on the right side. And this actually gets widened if you are making it in reverse bias. And built-in potential actually is being reduced in the forward bias by this V minus V0. V0 was the built-in potential. So the barrier is actually reduced. And this barrier is widened if you are making it in reverse bias, V0 plus V. So if the barrier is getting widened, it means the current flow is being stopped. If the current flow is being stopped, it means in the reverse bias, it is going to work like the off switch. In the forward bias, it is going to work like the on switch. So there is the IV characteristic equation, which is derived for diode. And this equation comes like this. I is equal to IS. IS is the diffusion current. Okay. Exponent of QV upon KT minus 1. So when V is equal to 0, you can see IS into V is equal to 0 means exponent of 0. That becomes 1 minus 1. There is no current flowing when V is equal to 0. Okay. KT by Q is the thermal voltage. At room temperature, it is 25.8 millivolts. It is represented by VT. That's the thermal voltage, and it is represented by VT. And this thermal voltage actually is somehow coming into the picture because it has the effect on the electrons, holes, the generation, and with respect to temperature, how that probability of Fe is being changed. All these things are actually controlled with the help of temperature. So this thermal voltage is very much important with respect to that thing. So this IS is equal to exponent of VD upon VT minus 1, right? So these are the characteristics. In the forward bias characteristics, as I told you, that's the threshold voltage or knee voltage or cutting potential of the diode. For silicon, it is seen 0.7, and for germanium, it is seen 0.3. For silicon, the cutting voltage represented by V gamma, it is also called as knee voltage, cutting voltage, or threshold voltage, you can see. V gamma, we can represent it by V gamma. Okay, so till that, V minus V0 or V gamma. V gamma is V0, what we discussed. So till that, electrons are not ready to move so well. After that, electrons are moving more and more and more. So you can see the current on the y-axis is going to increase after that. On x-axis, it is the voltage, that is nothing but VD, diode voltage. And this is the reverse bias condition. In the reverse bias, the scale has been changed. This is the expanded scale. So on the forward bias, we will be taking milliamperes, while in reverse bias, you can take nanoamperes, microamperes, like that you can take. So you can see this is going to increase very slowly. So this is nothing but the I0 IS current, which is nothing but the reverse bias saturation current, which is basically because of the diffusion. This current is represented by IS, that is nothing but the diffusion current. Now, what is this VZK? This is known as the breakdown. So it is the breakdown condition. We should always avoid the breakdown. So we also call this as, there is PIV rating, peak inverse voltage. Peak inverse voltage is nothing but this voltage, and we should only operate our diode in this particular region. We should not go beyond this. If we are going beyond this, then the ions actually will get abruptly actually come out of their original position, and because of that, uncontrollable current is going to flow, and that is the breakdown. You cannot expect to work that device again. Yes, you cannot expect the device to work again in the similar condition. So that's what we have to make sure, that our diode is operating only in this particular region before the PIV rating, or the we also call this as avalanche breakdown. Avalanche means sudden actually bombarding. Avalanche means sudden. For example, you might have heard the news. In Tehri, there was avalanche of some hills or something like that. So that is sudden coming away from their original position. So that is actually destructive. We have to avoid that destruction. If we are not able to avoid that, that means the device cannot operate in the normal condition again. So that is known as the avalanche breakdown, that is seen in the normal PN junction diode. Now, the other things related to this will be taken by our next speaker, Professor Anand Gulusu from IIT Roorkee. If you have any questions so far, do you have any questions? Please type in the chat box if you have any questions. Please type in the chat box. Am I audible? Am I audible? Okay, okay, sir. हाँ, yes, sir, yes. Yes, sir, yes, sir. Oh, सर अभी मैंने पीएन जंक्शन डायोड कवर